All right, so welcome back to Crafting Interpreters in Rust. Today we're just reading chapter 9, and we'll probably structuring the code for it about how to interpret control flow statements. So start reading. Control flow. Compared to last chapter's grueling marathon, today is a lighthearted frolic through a daisy meadow. But while the work is easy, the reward is surprisingly large. Right now, our interpreter is little more than a calculator. A LOX program can only do a fixed amount of work before completing. To make it run twice as long, you have to make the source code twice as lengthy. We're about to fix that. In this chapter, our interpreter takes a big step toward the programming language major leagues, Turing completeness. Turing machines. In the early part of last century, mathematicians stumbled into a series of confusing paradoxes that led them to doubt the stability of the foundation they had built their work upon. To address that crisis, they went back to square one. Starting from a handful of axioms, logic, and set theory, they hoped to rebuild mathematics on top of an impervious foundation. They wanted to rigorously answer questions like, can all true statements be proven? Can we compute all functions that we can define? Or even the more general question, what do we mean when we claim a function is computable? They presumed the answer to the first two questions would be yes. All that remained was to prove it. It turns out that the answer to both is no, and astonishingly, the two questions were deeply intertwined. This is a fascinating corner of mathematics that touches fundamental questions about what brains are able to do and how the universe works. I can't do it justice here. What I do want to note is that in the process of proving that the answer to the first two questions is no, Alan Turing and Alonzo Church devised a precise answer to the last question, a definition of what kinds of functions are computable. They each crafted a tiny system with a minimum set of machinery that is still powerful enough to compute any of a very large class of functions. These are now considered the computable functions. Turing's system is called a Turing machine. Church's is the lambda calculus. Both are still widely used as the basis for models of computation, and in fact, many modern functional programming languages use the lambda calculus at their core. Turing machines have better name recognition. There's no Hollywood film about Alonzo Church yet, but the two formalisms are equivalent in power. In fact, any programming language with some minimal level of expressiveness is powerful enough to compute any computable function. You can prove that by writing a simulator for a Turing machine in your language. Since Turing proved his machine can compute any computable function by extension, that means your language can too. All you need to do is translate the function into a Turing machine and then run that on your simulator. If your language is expressive enough to do that, it's considered Turing complete. Turing machines are pretty dang simple, so it doesn't take much power to do this. You basically need arithmetic, a little control flow, and the ability to allocate and use theoretically arbitrary amounts of memory. We've got the first. By the end of this chapter, we'll have the second. So conditional execution. Enough history, let's jazz up our language. We can divide control flow roughly into two kinds. Conditional or branching control flow is used to not execute some piece of code. Imperatively, you can think of it as jumping ahead over a region of code. Looping control flow executes a chunk of code more than once. It jumps back so that you can do something again. Since you don't usually want infinite loops, it typically has some conditional logic to know when to stop looping as well. Branching is simpler, so we'll start there. C-derived languages have two main conditional execution features, the if statement and the perspicaciously named conditional operator, ? Oh, no, it's like a ternary. An if statement lets you conditionally execute statements, and the conditional operator lets you conditionally execute expressions. For simplicity's sake, LOX doesn't have a conditional operator, so let's get our if statement on. Our statement grammar gets a new production. All right. So an if statement has an expression for the condition, then a statement to execute if the condition is truthy. Optionally, it may also have an else keyword and a statement to execute if the condition is falsy. The syntax tree node has fields for each of these three pieces. Like other statements, the parser recognizes an if statement by the leading if keyword. All right. So we actually we did this in a weird order. We did like the entire parser, and now we're doing the evaluation like chapter by chapter. But the book does like parsing, evaluation, parsing, evaluation, parsing, evaluation. So I've generally been skipping reading the parts about how to parse something because we've already done it. So I will do that. All right, so parsing, yeah, you just recursively call expression, statement, and then see if else exists, and then call statement again. All right. So that seemingly innocuous optional else has in fact opened up an ambiguity in our grammar. Consider if first, if second, when true, else when false. Here's the riddle. Which if statement does that else clause belong to? This isn't just a theoretical question about how we notate the grammar. It actually affects how the code executes. If we attach the else to the first if statement, then when false if is called if first is falsy, regardless of what value second has. If we attach it to the second if statement, then when false is only called when first is truthy and second is falsy. Since else clauses are optional, and there is no explicit delimiter marking the end of the if statement, the grammar is ambiguous when you nest ifs in this way. This classic pitfall of syntax is called the dangling else problem. It is possible to define a context-free grammar that avoids the ambiguity directly, but it requires splitting most of the statement rules into pairs, one that allows an if with an else and one that doesn't. It's annoying. Instead, most languages and parsers avoid the problem in an ad hoc way. No matter what hack they use to get themselves out of the trouble, they always choose the same interpretation. The else is bound to the nearest if that precedes it. Our parser conveniently does that already. Since if statement eagerly looks for an else before returning, the innermost call to a nested series will claim the else clause for itself before returning to the outer if statements. Okay. Yeah. Syntax in hand, we are ready to interpret. All right, so here's how to visit an if statement. The interpreter implementation is a thin wrapper around the self-same Java code. It evaluates the condition. If truthy, it executes the then branch. Otherwise, when there is an else branch, it executes that. If you compare this code to how the interpreter handles other syntax we've implemented, the part that makes control flow special is that Java if statement. Most other syntax trees always evaluate their subtrees. Here we may not evaluate the then or else statement. If either of those has a side effect, the choice not to evaluate it becomes user visible. Okay. All right. Since we don't have the conditional operator, you might think we're done with branching, but no. Even without the ternary operator, there are two other operators that are technically control flow constructs, the logical operators and an OR. These aren't like other binary operators because they short circuit. If after evaluating the left operand, we know what the result of the logical expression must be, we don't evaluate the right operand. For example, false and side effect. For an AND expression to evaluate to something truthy, both operands must be truthy. We can see as soon as we evaluate the left false operand that it isn't going to be the case. So there's no need to evaluate side effect and it gets skipped. This is why we didn't implement the logical operators with the other binary operators. Now we're ready. The two new operators are low in the precedence table. Similar to OR and 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 C, they each have their own precedence with OR lower than AND. We slot them right between assignment and equality. I think we actually have to change this. We just implemented it straightforwardly without short circuit. Instead of falling back to equality, assignment now cascades to logic OR. The two new rules, logic OR and logic AND, are similar to other binary operators. Then logic AND calls out to equality for its operands, and we chain back to the rest of the expression rules. We could reuse the existing expr.binary class for these two new expressions since they have the same fields. But then visit binary expr would have to check to see if the operator is one of the logical operators and use a different code path to handle the short circuiting. I think it's cleaner to define a new class for these operators so that they get their own visit method. To weave the new expressions into the parser, we first change the parsing code for assignment to call OR. Okay. The code to parse a series of OR expressions mirrors other binary operators. All right. Where did this actually change? Assignment. Okay, so this is just, he's fitting it into the precedence rules. Okay, we've already done this. All right. If you compare this to the earlier chapter's visit binary expr method, you can see the difference. Here we evaluate the left operand first. We look at its value to see if we can short circuit. If not, and only then, do we evaluate the right operand. All right. So, okay, yeah. So they're handling both the same way. It's just that they're handling both in the same visitor. It's just that what they do depends on whether it's what they do for short circuiting depends on if it's OR or AND. All right. The other interesting piece here is deciding what actual value to return. Since LOX is dynamically typed, we allow operands of any type and use truthiness to determine what each operand represents. We apply similar reasoning to the result. Instead of promising to literally return true or false, the logic operator merely guarantees it will return a value with appropriate truthiness. Fortunately, we have values with proper truthiness right at hand, the results of the operand themselves. So we use those. For example, print high or 2. All right, it's just printing. Yeah. Showing the short circuiting. On the first line, high is truthy, so the OR short circuits and returns that. On the second line, nil is falsy, so it evaluates and returns the second operand, yes. That covers all of the branching primitives in LOX. We're ready to jump ahead. All right, that's cheesy. I'm not going to read that. So, while loops. LOX features two looping control flow constructs or statements, while and for. The while loop is a simpler one, so we'll start there. The grammar is the same as in C. We'll add another clause to the statement rule that points to the new rule for while. It takes a while keyword followed by a parenthesized expression or condition expression, and then a statement for the body. That new grammar rule gets a syntax tree node. All right, he's talking about parsing. All right, and here's how you visit while. Again, you're just borrowing the while from Java because they've already implemented it. Okay. All right, we're down to the last control flow construct, yield C-style for loop. I probably don't need to remind you, but it looks like this. Okay. So for, it's going to be a var declaration or an expression or a semicolon, and then an optional expression for the exit condition and an statement. I guess, that's interesting that that's an expression. I think of that as a statement, but maybe it's an expression because not everything can go there. Okay. I guess we'll talk about it. All right, inside the parentheses, you have three clauses separated by semicolons. First clause is the initializer. It is executed exactly once before anything else. It's usually an expression, but for convenience, we also allow a variable declaration. In that case, the variable is scoped to the rest of the for loop, the other two clauses in the body. Next is the condition. As in a while loop, the expression controls when to exit the loop. It's evaluated once at the beginning of each iteration, including the first. If the expression is truthy, it executes the loop body, otherwise it bails. The last clause is the increment. It's an arbitrary expression that does some work at the end of each loop iteration. The result of the expression is discarded, so it must have a side effect to be useful. In practice, it usually increments a variable. Any of these clauses can be omitted. Following the closing parenthesis is a statement for the body, which is typically a block. Desugaring. That's a lot of machinery, but note that none of it does anything you couldn't do with the statements we already have. If for loops didn't support initializer clauses, you could just put the initializer expression before the for statement. Without an increment clause, you could simply put the increment expression at the end of the body yourself. In other words, LOX doesn't need for loops, they just make some common code patterns more pleasant to write. These kinds of features are called syntactic sugar. For example, the previous for loop could be rewritten like so. This script has the exact same semantics as the previous one, although it's not as easy as on the eyes. Syntactic sugar features like LOX's for loop make a language more pleasant and productive to work in, but especially in sophisticated language implementations, every language feature that requires backend support and optimization is expensive. We can have our cake and eat it too by desugaring. That funny word describes a process where the front end takes code using syntax sugar and translates it to a more primitive form that the back end already knows how to execute. We're going to desugar for loops to the while loops and other statements the interpreter already handles. In our simple interpreter, desugaring really doesn't save us much work, but it does give me an excuse to introduce you to the technique. So, unlike the previous statements, we won't add a new syntax tree node. Instead, we go straight to parsing. Okay. First, we'll add an import we'll need soon. Right. Like every statement. Okay. I think we did this, the way we did this is just like everything else. We just had it generate a syntax tree node. But this is fine too. So he's just turning it into the abstract syntax tree version of this. Okay. Etc. Okay. That's it. Our interpreter now supports C-style for loops, and we didn't have to touch the interpreter class at all. Instead, we desugared to nodes the interpreter already knows how to visit, so there's no more work to do. Finally, LOX is powerful enough to entertain us, at least for a few minutes. Here's a tiny program to print the first 21 elements in the Fibonacci sequence. All right, cool. We can use this as a test, maybe. All right, I usually do not read these because they're just like take-home exercises, but I do read these. All right, design note, spoonfuls of syntactic sugar. When you design your own language, you choose how much syntactic sugar to pour into the grammar. Do you make an unsweetened health food where each semantic operation maps to a single syntactic unit, or some decadent dessert where every bit of behavior can be expressed 10 different ways? Successful languages inhabit all points along this continuum. On the extreme acrid end are those with ruthlessly minimal syntax like Lisp, Forth, and Smalltalk. Lispers famously claim their language has no syntax, while Smalltalkers proudly show that you can fit the entire grammar on an index card. This tribe has the philosophy that the language doesn't need syntactic sugar. Instead, the minimal syntax and semantics it provides are powerful enough to let library code be as expressive as if it were part of the language itself. Near these are languages like C, Lua, and Go. They aim for simplicity and clarity over minimalism. Some, like Go, deliberately eschew both syntactic sugar and the kind of syntactic extensibility of the previous category. They want the syntax to get out of the way of the semantics, so they focus on keeping both the grammar and the library simple. Code should be obvious more than beautiful. Somewhere in the middle, you have languages like Java, C#, and Python. Eventually, you reach Ruby, C++, Perl, and D, languages which have stuffed so much syntax into their grammar, they are running out of punctuation characters on the keyboard. To some degree, location on the spectrum correlates with age. It's relatively easy to add bits of syntactic sugar in later releases. New syntax is a crowd pleaser, and it's less likely to break existing programs than mucking with the semantics. Once added, you can never take it away, so languages tend to sweeten with time. One of the main benefits of creating a new language from scratch is it gives you an opportunity to scrape off those accumulated layers of frosting and start over. Syntactic sugar has a bad rap among the PL intelligentsia. There's a real fetish for minimalism in that crowd. There is some justification for that. Poorly designed, unneeded syntax raises the cognitive load without adding enough expressiveness to carry its weight. Since there is always pressure to cram new features into the language, it takes discipline and a focus on simplicity to avoid bloat. Once you add some syntax, you're stuck with it, so it's smart to be parsimonious. At the same time, most successful languages do have fairly complex grammars, at least by the time they are widely used. Programmers spend a ton of time in their language of choice, and a few niceties here and there can really improve the comfort and efficiency of their work. Striking the right balance, choosing the right level of sweetness for your language, relies on your own sense of taste. Okay, all right. That's chapter 9. Now we can go ahead and start porting it. Okay. So because we've already written the parser for for loops, I don't think we should do the same desugaring thing. I think it's just as easy to like write evaluation logic for it separately. Okay, but first off, let's do the if statement. Okay. So did we have if statements encoded? Yes, we do. Okay. So add this case here. All right. Okay, this won't return anything, I think. Just executes the if statement. So we need to evaluate the condition. Let's see. Condition is an expression. And then we get the state in from here. All right, see how it likes that. And did we have a truthiness thing written? I kind of forgot. We called it truth value. I'll just then we do, so the if case is a statement. We interpret statement if case state else. Oh, and there's an optional else. So else case is a box option statement. Okay. All right, now let's fix what it's complaining about this condition. All right, this is a box. Let's see, a box is like, I do that. Yeah. All right. Now this is a value instead of a reference to a value. And this is a box again. This is, there we go. Okay. I think that's if. You can go ahead and write a test or something. Test. Um, okay. I'll get back to that. I think there's a few other easy things I can do. Um, and the thing that he was talking about with dangling else, I think is already taken care of from parser. I'm not sure. We can test it. Okay. While's easy. So you're gonna do while truth value evaluate addition. Interpret statement body. Why do you have to return null? I kind of forgot why he has to return null in visitors. I guess they all like return. So both just oh, okay. Wait, that didn't work. Why did that not work? Is it because I used the wrong thing there? Yeah. Okay. Use of moved value.
You can try cloning it, or we can look into passing them by reference.
Mm-hmm.
For now, we can start cloning everything.
Yeah. Why does this need to, why does a val expert need to consume the expression actually?
I think we started this way initially. There is no specific reason, but when expression is a single string constant, you need to return it as it is. But maybe we use clone there instead of all over the place.
Okay.
So we can look into optimizing that later.
Yeah.
Or
I'll just clone it now. Let's see. Do we have, wait, does this even, can I derive clone for expression?
Should be possible.
Let's see. What's the problem there? Expression cannot be zero. Okay. I think that's right, right? No.
You don't need star on line 168, I think.
Do I need to clone it like repeatedly? I shouldn't, right? I guess it'll consume it.
You evaluate it multiple times, so yes,
Yeah.
you do.
Okay. Use of moved value, same thing here. All right.
Yeah. Same for body.
All right, that's fine for now. Yeah. Okay. All right, cool. So that's while. And we needed to change how the logical operators get evaluated. Because we don't want to evaluate both actually. So I'll check for those first, I think, right? Because I know if the operator is logical operator here.
You need to evaluate left regardless.
Sure. Okay. I'll put it here. So if it's one of them, I'll do what he does in the so this, don't do anything.
I think an easy way would be just to copy evaluation right into corresponding branches. So you have one big match statement, and eval right is called multiple times, well, in multiple branches.
All right. That seems ugly to me, but that's fine. Okay, so yeah, like this.
Yeah. Well, it's either this or inexhaustive match and some ugliness.
Yeah.
It handles some of them before and after. And I
Sure.
find that you add more cases to branches every once in a while. And once you do, compiler won't be able to help you.
I mean, it's really ugly.
It's not that bad.
All right. So here, finally, we don't need to copy that line. We need to, if truth value left, this is an or, so if this is true, then you just return true. Wait, does this return? Yeah. Value equal true. And then otherwise return this. And we would need to evaluate it in that case.
Maybe if you're unhappy with calling eval multiple times, you can try to shove eval expression inside pair of numbers. We call it on every case where we care about it. But I don't think it matters much.
Because so a pair of numbers would just do the eval expert for left and right. Yeah. I don't know. We can think about it later. All right. So this should have sort of the same structure. So if not truth value left, then return false. Otherwise, return the right. I think that's right. Good check.
Yep.
So if it's or, if it's truthy left, return left. Oh, okay. So interesting. He's returning what's on the left instead of true. So I think that's, yeah. Which is interesting. Like this, yeah.
I am not sure if it's a good idea, but maybe
Yeah, neither.
the language is designed to be strange. We should be able to return the same.
Well, that's what it does. If you do this with two things that are Booleans already, it's operates like normal. Let me see what, okay. Does JavaScript do this?
JavaScript does something horrible with those. Yeah.
Yeah, okay. Wait, 5 is, oh, okay. What I meant was this. Okay, JavaScript does the same thing. Does Python do the same thing?
Python is not the smartest language either.
Yeah, I'm just, yeah, seeing how weird this is. It looks like it's normal for these dynamically typed things. Okay, so we're not returning truth value, we're just returning this. And then never evaluating the truthiness. Okay. Okay. But then these ones are definitely bools. Yeah, I think. Okay. That distresses me, but it's what the language asks for. All right. So we have logical stuff, if, while, and then let's do a for loop. So I'm not going to do what he does.
Should we write a small test for a while statement?
Sure. Yeah. I'll write some tests for all of these things. Okay. So let's do if. Yeah, I don't know if he requires parentheses. Let's see. All right, I kind of want, I want to start writing these tests as just like one's literal. Do we have a function that will do that yet? Have this.
Okay. Well, we have a way to parse it in the program, I think, and we should be able to have something to evaluate the program. It's just okay right now.
Yeah, I guess that, yeah, it's the parser part that I don't know.
Parse string with should be able to deal with parsing the program as well.
Like this?
Yeah.
All right, so I want var a equals 1. And then we can still put in an environment and then use the environment to track the results. I forgot why I made it evaluate this instead of, oh, that's to see if it properly references the environment. But here we can just directly check the value of A. Okay. A equals 2 else. Semicolons. A equals 3. Okay. And then, so interpret that. We actually get, and so this is a program. So it's not a vector of declarations yet. So that means to pass it into interpret, we need to get those out. I'm pretty sure a program just is that. Yeah, okay, it's dot body. Right. It's not pub. So what we want is env dot get A equals value number 2, I believe.
Probably unwrap. I would add, no, it works. Okay. That's unusual.
It's unusual for us to compile slowly.
No, you updated the compiler, remember? It's not supposed to compile this long unless you have some kind of potato PC.
Okay. I go test. All right. Insertion failed.
It's better not to use assert if you're trying to assert equality. You just use assert eq. If it's not matching, it will print.
I'll print what it is.
What the value was.
All right.
It's false. Yeah. it actually better
I guess
math
I
for
meant I
you.
just wrote the test wrong, didn't I? Yeah.
Yeah,
Okay.
good. It works.
Nice. Okay. This is a good general program or a general pattern for the test, I think. So let's do a while test. So while a less than 6, a plus equals 1. And then at the end of it, a should be 6.
I hope so.
Okay.
Fails to parse.
Fails to parse. Okay. Do we have plus equals? I kind of forgot.
We don't. We do not. We do have a
Hmm.
plus 1.
Okay. Wait, I kind of thought that we added that. Let me see. Maybe I just imagined it. It would be in, yeah, we don't.
Tokenizer. It
Yeah,
would be in tokenizer.
yeah, we don't have like a plus equal or anything. Okay. Cool. So I think we're good then.
Yeah, making progress.
And then let's see. I can test short circuit somehow.
I don't think you can. Unless it's like a function. You need something that gets evaluated,
Yeah.
but
Well, does he have an example here? Yeah, I need to, it doesn't let, he doesn't let you treat a whole block as an expression. So I can't say like, var b equals 2 and then have the second thing in the and be like b equals 3.
okay,
No, I
we
can do
can
that.
we
I can do
can
that.
we can try using invalid variable in the second branch if it's
Sure.
shortcut and it's not going to access.
Sure.
By the way, let's try to access invalid variable, see what it does.
Sure. Yeah. Print C.
Do we have C? Do we have print?
Yeah. Oh, have we implemented it? I think so. Yeah.
Oh, we do. Awesome. It's not going to make a good test though. Bad get.
So why is it printing all this parser crap? Did I leave? Okay.
Possibly.
Um, bad get. So just prints bad get. That's funny. All right. I think we did sort of just kick that down the road, like making those
Yeah.
error messages good. Yeah. Okay. All right. So to test short circuit. Var B equals A and
No, you need or. A or C.
A or C. All right. So then B should equal 1.
What?
Yeah, he doesn't use the pipes. He uses the word or.
Okay. Okay, that works.
Okay. We tested or. Now let's test and. So can we test and? We need to. So here it's like false. False.
You need to change the condition, yeah. Yeah, looks about right.
Cool. Okay. And I think that's probably it, unless we can do for loops really fast. Let's try to do for loops really fast. Nah, whatever. I'll just call it. All right. Cool. So this is, oh, let me make sure I am up to date. This is if while short circuit or and or. Okay, cool. We'll call it there.